We are discussing about Euler's theorem for homogeneous function. So today we will discuss about the corollary and the deductions of Euler's theorem. So we start with the corollary. So here we write down the corollary of homogeneous function. So we have if z be the homogeneous function of x and y of degree n, so then we have a first corollary. So first corollary is x del square u upon del x square plus y del square u upon del x del y is equal to n minus 1 del u upon del x. Okay, so here we can take the value of z is u. We can understand by taking u. Second corollary, so we have x del square u upon del x del y plus y del square u upon del y square is equal to n minus 1 del u upon del y. And the third corollary, so third corollary, you can give as this as equation number first, you can give as this equation number second, and we add by multiplying equation first with x and second with y and adding, so we get the third corollary. So that will be x square del square u upon del x square plus 2xy del square u upon del x del y plus y square del square u upon del y square is equal to n minus 1 into u. So these three are corollaries. You can easily prove that corollaries. So we can prove the corollaries also. So here is the proof. So we have written there that u be the homogeneous function. So given u be the homogeneous function, of degree n. So we write down as u is equal to function of x, y. So then the Euler's theorem. So we shall prove this by using the Euler's theorem. So then the Euler's theorem is x del u upon del x plus y del u upon del y is equal to nu. So we can give as equation number third. Okay, so differentiate third partially with respect to x. So we see that here in first term, there are two functions of x. So we do the differentiation partially. So first function and differentiation of second with respect to x. So we write down as del square upon del x square plus differentiation of first, that means the differentiation of x is 1. We write down as second as it is plus. So y be the constant term. When we are going to differentiate partially with respect to x, so y treat as a constant. So in first time, the derivative is 0, and we write down del u upon del y plus y, and differentiation with respect to x is del x into del y is equal to n, and differentiation of u with respect to x del u upon del x. So this del u upon del x we can take into our RHS side. So we see that x del square u upon del x square plus y del square u upon del x into del y is equal to n del u upon del x minus del u upon del x. So this gives us n minus 1 del u upon del x. So this is our first corollary we have proved. So now similarly we prove the second corollary. So we write down proved. Now move to the second corollary. For second corollary, so we write down as differentiate equation third partially with respect to y. So we write down as first when we are doing a partial differentiation with respect to y, so x we treat as a constant. So we write down as x into del square u upon del y del x plus differentiation of x is 0 into del u upon del x plus differentiation y we write as it is, and the differentiation of del u upon del y is del square u upon del y square plus differentiation of y is 1, and we write down second term as it is. So this equal to n del u upon del y. So same, we take a del u upon del y into RHS side, and we have a del square u upon del y del x is equal to del square u upon del x del y. Okay, so we write down as x square or x del square u upon del x del y plus y del square u upon del y square is equal to n del u upon del y minus del u upon del y. So this gives us n minus 1 del u upon del y. So this is our second corollary. So we have proved. Now we shall prove the third corollary. So by proving the third corollary, so we give as equation number 4 to this one, and equation number 5 to this one. And we move further. That means multiply 4 by x and 5 by y and adding. So we get the first term will be x square del square u upon del x square plus xy del square u upon del x del y plus x y del square u upon del x del y plus y square del square u upon del y square is equal to n minus 1 x del u upon del x plus n minus 1 y del u upon del y. So we add these two terms. So we write down as x square del square u upon del x square plus 2xy del square u upon del x del y plus y square del square u upon del y square is equal to. So we take n minus 1 as common from both the terms. So we have x del u upon del x plus y del u upon del y. So this gives us nu. So we write down n minus 1 into nu. Okay, so here we have taken this from third equation. So we write down as using 3. So using third. So this is the third corollary parts. So we have proved now. After corollary, we move to very important deductions. So now we write down the important deductions. Important deductions. So we get from Euler's theorem. So we have first deduction. So by using Euler's theorem, we have x del u upon del x plus y del u upon del y is equal to nu. Okay, so here u is given in the form of the function, that means fu form. So when u is given in the form of function fu form, so then we can write down as x del upon del x into fu. We replace u by fu plus y del upon del y into fu is equal to nfu. So when we differentiate this fu with respect to x, because u is also the function of x, so you can see that. So f dash u, differentiation of fu with respect to x, we write down as f dash u into del u upon del x plus y, again f dash u with respect to y, or del u upon del y is equal to nfu. So we can take common f dash u. So we have x del u upon del x plus y del u upon del y is equal to nfu. So we write down the first deduction as x del u upon del x plus y del u upon del y is equal to n f u upon f dash u. So this is our first deduction. This is our first deduction. So we have to remember some in some problems related to Euler's theorem, we have used this first deduction. Okay, so hope you understand this first deduction. Now we also have a second deduction. So for second deduction, we have second derivative. So by using the second derivative, we shall prove the second deduction. So for the second deduction, we